All right, guys, let's keep it going. So it says question 3.6, which of the following statements is not true about correlation between the length in inches and weight in pounds of a sample of brook trout? Okay, so maybe you have, 10-inch fish, 20-inch fish, 30-inch fish, who knows? And wouldn't that correlate to how many pounds it is, right? 5 pound, 10 pound, 15, maybe it would make some dots like this, right? Which of the following would not be true about R? First, we know this is true, right? We talked about this. Then R says measure in inches. Our notes say R has no units, no labels. All right, when we calculated R by hand, it's the distance a number is from the line, the average distance, right? Right, so it's like it can't be in, it can't have any units. Also, we know that if we flipped inches and pounds, R would stay the same. So if R here is 0.08, or 89, let's say it's a moderately strong linear relationship between inches and pounds in the trout. And then we flip-flop these X and Y axes, put inches here and pounds here, right? We know that the slope would change, right? But the distance the dots are away from the line would be the same and R would stay the same. So again, this tells us R has no units. So that is our answer. R has no units. That has to be false. It's not measured in units. What would be C? If a longer trout would also tend to be, a larger trout would be heavier. If R is positive, yes. If it's a positive association, the bigger the trout, the heavier it would be. R would not change if we measured the length of the trout in centimeters and inches. Yeah, once again, these don't have units. So if I change this to centimeters, R wouldn't change. So that's true. And this is true. R would not change if we measured the weight in kilograms. Yeah, once again, whether you measured it in pounds or kilograms, R is not changing. It doesn't have anything to do with that. It's because when we calculate it by hand, we divide by pound or inches divide by inches, and all the units cancel out. All right, question number 33.7. It says, when we standardize the value of a variable, the distribution of standardized values has a mean and a standard deviation, a mean of 0 and a standard deviation of 1. That's correct. We learned that last chapter. Suppose we measured two variables, x and y, on each of several subjects. We standardize both variables and then compute the least squared regression line. Suppose the slope of the least squared regression line is negative 0.44. So that would be a picture. So the dots are going kind of down, left to right. Not super close to the line of best fit. So maybe that would look like an R of negative 0.44, right? So now they ask, suppose the slope of the least squared regression line is, oh, I'm sorry, I misread that. Sorry about that. We standardize both variables, then compute the least squared regression line. All right. And suppose the slope is negative. Okay. So what does that mean? What that would mean is, in a weird way, since we standardized everything with a mean of 0, right? right? And these would be, greater than that or less than that. And these would be greater than that and less than that. In a weird way, that is exactly what R would be, and that's why I accidentally wrote that down. In a weird way, that would be the slope of the line, so that is exactly what R is if we standardized both of the variables, meaning eliminated both of the units, that in fact would be, and so that would be our correlation, although we don't think of correlation in that way. That's an interesting question. All right, let's look at number 3.8. It says a linear relationship between the number of chirps made by the stripped ground cricket and the air temperature. A least squared fit of some data says that we have a model. Y hat is the estimate temperature in degrees Fahrenheit. Okay. All right, and so here's my line of best fit. X is, well, it says like, what am I going to use to predict that? X is the number of chirps per minute. So this is totally true. This is out of real life. We're saying this has a positive slope. So as you hear more chirps, we get in warmer weather. So that's why in the summertime, when you go outside, you hear all these crickets. When it's cold outside, the crickets are hibernating. So there is a correlation between how many chirps you're hearing and the temperature. And the higher the temp, the more the chirps, or the more the chirps, the higher the temp, right? What is the predicted increase in temp for an increase in 5 chirps? Okay, so what is the predicted increase in temp for an increase of 5 chirps? So the slope here is that. And what is the slope? Well, the slope is the change in Y over 1 change of X. So 1 additional chirp per minute. So this is saying I'm going to get 3.3 extra degrees Fahrenheit for every 1 chirp. So how many would I get if I have 5 chirps per minute? Well, these have to be equivalent fractions, right? So here I multiplied by 5. So this would just be 5. So I hear 1 more chirp per minute. The temperature goes up 3.3, and then another, and then another, and then another. So just 5 more of those in a row. And we're going to get 3.3 times 5. So this would be choice B, right? 16.5 degrees Fahrenheit. Cool. 2 more. Let's see. 3.9 says, a scatter plot shows the relationship between the number of people per TV and the number of people per physician. Interesting. Along with the least squared regression line, in Ethiopia, there were 500, so this must be Ethiopia. There were 503, so that's how I know that was Ethiopia, and 36,000 people per doctor. Oh my goodness, right? They do not have very good health care. Which of the following would be correct? All right, so it says Ethiopia has more people per doctors than expected based on how many people it has TV. Yes, they're essentially saying that it is about, this is where for that number of people per TV, we would predict them to have 15 people per doctor, but they have over 36,000 people per doctor. So E has to be our answer. Ethiopia has more people per doctor than expected. The correlation is greater than 1, never, right? No. The slope of the least squared regression line is less than 1. No, it's positive. So the R is greater than 0. Oh, wait, I'm sorry. It says the slope of the least squared regression line is less than 1. Let's see our slope here. Looks like our slope is looks like I went changing my rise over run, right? So I went up 15,000. I went over 500. This is definitely a number greater than 1. Right? Way greater than 1. So it's less than 1? No. The slope. Increasing the number of TVs will attract more doctors. When they say this sounds like causation, and we want to say causation never. The point for Ethiopia is decreasing the slope. Okay, so let's get my magic pen. If this is it, with Ethiopia there, it's not increasing the slope, it's pulling it toward that number. So without Ethiopia up here, the slope would have been probably more like this. You see what I'm saying? So it's pulling it towards it. It's increasing the slope. So we know this one's false. And again, we know E is right. But this would be the word increasing. So it's pulling the line closer to it. Therefore, it's increasing the slope than it would have been without that point. Okay, last question, D. The scatter plot shows the lean body mass and metabolic rate for a sample of 5 adults. Okay, 1, 2, 3, 4, 5. For each person, the lean body mass is the subject's total weight in kilometers or kilograms, less any weight due to fat. The metabolic rate is the number of calories burned in 24 hours. Okay. Because a person with no lean body mass should burn no calories, it makes sense that the model the relationship with a direct variation function in the form y equals kx. All right. Models were tried using different values of k, and the sum of the squares was calculated for each value k. Here is a scatter plot showing the relationship. Okay, so we see that this forms a U, okay? So if this question was on the test, this would be considered bonus because this is something that looks non-linear. It looks like it's behaving differently, right? So according to the scatter plot, what is the ideal value of K to use for the predicted metabolic rate? It's showing here we would use $29, right? Because the sum of the squares of the residuals would be the lowest. We want a least squared regression line needs to minimize the area under the curve, right? And the area above the curve. So it has to minimize the sum of the squares. All right. I think that's enough for one day. I might make, here's a question 11. Snuck it in here. One more. Okay, let's take a look. Yeah, this one would be bonus because it's a log one. So let's see. We would say we recorded this data. The scatter plot revealed it was definitely curved. This is a base 10, so I'd use a log calculator. The least square regression line says this. Based on this, which of the following would be the best estimate for a population in year 2020? Okay, so we're just going to plug this in and then plug it in our calculator, right? They want to know my prediction. So my prediction, the log of my population, would be negative 13.5 plus 0.01, and I'm going to multiply by 2020. So plugging that into a calculator. We get 2020 2020 times 0.01. And then we're just going to subtract 13.5. So how do we get rid of log, and how do you know how to get rid of it? Again, this would be bonus, but we're just, helping people out. If we're helping people remember if they had this before. So we have to get an advertisement, of course. If we see this log of 10 and I hit the second button, right? We see the log, then we can find the inverse log. So that's to 10, something to the power of 10. So that's how I undo log. We notice that on our fancy calculators. So see how it reminds you on just this basic calculator, log is base 10. So if we go here, how do we get rid of log? I'm going to take it to the power of 10 on both sides. Okay, so the 10 to the power of log of population would just be the inverse of an operation, would just leave you population on the left. And here on the right, I'm going to put 10 to the power of 6.7. So 10 to the power of 6.7, we get 5 million. So we go back to our question and we get did I type that in wrong? Probably. 10 to the power of 6.7. Oh, that's weird. There's something wrong with my calculator. I'm sorry, guys. That should be this number, right? That's 10 to the power of 6.7. And that's our answer. Wait, what am I saying? Yes, okay, it's 5 million. That's right. It's not a scientific notation. It's just that number. That's right. Okay, and that's C. So we typed this in the calculator and we got approximately 5 million. And so then this is our answer. And again, this is bonus, but some students do understand how to take the inverse log and the log of numbers. So go ahead and give them some bonus for knowing that. It will also help you on the AP exam. Thanks, guys.